Hi, this is lesson 7, collision zones. So we're getting near the end of the plate boundaries. After this, we have conservative boundaries to look at, which there are two of, and there's also hotspot theory. That's relatively straightforward. So this is the last of the convergent boundaries. That's where they come together. So again, looking at a specification, which is really important to do, doesn't really show it on here, but it is a cause of fold mountains. So I just activate the laser pen. So we have definitely covered two types of destructive, two types of constructive. I haven't done anything on conservative plate boundaries, but when you've got fold mountains, you also need to realize there are two ways in which fold mountains are formed. One is on the destructive margins, which I talked about on the last lesson, the Andes Mountains, for instance, but also at a collision zone. I'll be explaining that very, very shortly, but you also get fold mountains with that. Himalayas are a great example of fold mountain formation, and this is a key feature formed at the collision zone. These are incredible. I don't know if you know this, but the mountains here have sedimentary rock, which has ocean fossils in it, and that is a huge indicator to tell us this mountain range was under the ocean millions of years ago, and it's going upwards. If you're not sure what the Himalayas are, we'll point that out in a second. So the Himalayas is over this zone here, and you'll see a more specific map in a minute. There are other collision zones like the Alps, for example, but I'm just going to focus on the Himalayas for this video presentation. So there we are. We're looking a little bit more closely, see with the laser pen where we're talking about, and you can see just rates of movement and things like that. And again, what's happening here, and you'll see this on the next slide, two plates are converging together, but something different happens. So the collision zone, convergence. So in the past, we've talked about one plate collides with another. One is usually denser, heavier than the other, and subducts beneath the other. In this situation, it's not so crystal clear. I don't think the diagrams make it ultra obvious. Certainly this one doesn't. So, but I would just keep this basic principle. Two continental plates are colliding. Neither, it looks like it does though, neither are subducting beneath each other, so they both push upwards. This area here is sedimentary rock that has been pushed upwards. You can see the indicator, the arrow there, being pushed upwards, heaved upwards. Okay, I think for the purposes of an exam question, keep it simple. Two continental plates of equal density push together, and they push sediment upwards, hence the mountain. So theoretically speaking, the Himalayas are getting higher, but they're also being counteracted by subaerial processes, erosion, being ground down. So yeah, there's a limit to how high they would get. In this picture, two plates are moving towards each other because of the convection cell theory we've talked about before. And just trying to bring it a little bit more alive here. Again, you can see if you look, you see this bit in here. Well, that looks like it's been subducted. Well, in this instance, that's the upper part of the mantle. So if you look at the crust part, they're pushing together. This zone here, and I'll talk more about this in the next lesson, the next slide. This section is actually getting closer together. So at one point that was much wider apart. That you see that gap there. It's what we call a geosyncline, and there was sediment in it, and that's what's being pushed upwards. Okay, so let's talk about what's going on, and I think these three stages are very, very useful to explaining what's taking place. Now, this again is a very loose kind of description of what's going on here. If I can't annotate like this I do on Zoom, because I'm running this live, but if I just hover this mouse around here, this section, you might argue, is sedimentary rock, and you'll see that more clearly on the next slide. Now, all of this would have been under the ocean, and it's been pushed upwards, squeezed upwards as the two plates have collided together. And if you imagine these two plates a little bit further apart, and again, where I'm just hovering with the mouse, if I just kind of feather that there would have been a shallow sea stroke ocean in that area, what we call a depression. We call it a geosyncline. and that would have been a shallow sea. And what runs off the land into the sea? Sediment. And it collects of layers, but then the two plates gradually have pushed together and they just uplifted that sediment to its current position. As I say, you go halfway up the Himalaya mountains, you can find fossils of ocean origin, which tells us they used to be under the sea. I find that quite incredible. You know, the world's tallest mountain, and it's used to be under the ocean. But the time scale of this, tens and hundreds of millions of years. But anyway, let's go back. That's quite an easy diagram to draw, especially if you do two-dimensional. But let's have a look at stage one. So what we're saying stage one, let's set the scene. So the key point from this, a long, long time ago, hundreds of millions of years ago, between the two plates, there was a huge depression called a geosyncline. There sat a sea, like a part of an ocean, shallow sea. Stage two, rivers coming off the land, put sediment into that sea, which was shallow, and you got layers of sediment, which then compacted, turned into hard rock, layers of rock. There's that bit there, compressing over millions of years into the sedimentary rock. Then, as the two plates got closer together, they got forced upwards, and they crumple, so they kind of bend, don't you, when you fold a piece of paper? So you get like what we call lots of folds. Now you see the same thing in the Andes mountains, but for different reasons. So just to repeat, there are two reasons why you get fold mountains. One because of the destructive margin, and the one because of the collision zone. Make sure you can make a clear distinction on that. Now this picture, again, I think nicely shows the pushing up of the sediment here. So you can see how this bit here would be wider at one point, and there may well have been an ocean there. There was. And you can see the layers of the sediment, which would have been horizontally laid down, but as they get compressed together, you can see the folding that takes place here. Okay, so the bending upwards of it. That, in essence, is all that I really need to talk about in this slide. On the next slide, I put one of those sheets on there so you can like draw a diagram of this, put a basic explanation, and then I'll run through to the end of the slide just to show you some extension work. I'm not going to read that out loud, but again, if you've got further reading that you'd like to do, these slides offer the opportunity to study folds, something called anticlines, synclines in a bit more depth, and a bit more specific information on the Himalayas themselves. You don't need it again, if you want to have an enriched amount of learning. This will be one of the shorter videos, by the way. So let's just move on. So again, like all of them, you could have a whole bunch of these, you know, from your constructive, destructive collision zone, and then going on to your conservative plate boundaries. Diagrams are always useful to have with labels and annotations, highlighting the key words that you need, and then this bit, particularly useful if you get a 4 marker. This is where almost like you model your answer, so put your answer in there. Subsequently, here are the extra bits of information you can read through. I'll just now come to quiet. Finally, just to recap, so in this lesson, this is convergence. Two continental plates move together, equal density. There was a shallow sea, a geosyncline in between, sediment formed there. As they collided and got closer together, they pushed the sediment upwards, causing fold mountains. Next lesson, lesson 8, we'll go on to conservative margins. And again, that's a relatively short video. I do feel the constructive and the destructive margins there's a lot more depth to it. And so subsequently, the end of the plate tectonic section will be a much, much quicker process. Okay, thank you for listening, and I'll see you at lesson 8.